Good morning. Welcome to Halloween's Tech Talk here. We thought we'd dress up as the scariest thing we could find, which is two language lawyers in front of a large room. There. So this is Matt Austern. He's going to be handling the second half of the talk, and I'm Lawrence Crowl. And we have a fairly whirlwind talk here. So what we'd like you to do is hold on to your questions until the end of the talk, because you might find that your question turns into something more interesting. And the other thing we'd like to ask is that if you can ask your question in a way that's not Google confidential, that would allow us to put the talk up on YouTube. So let's get started. And the first thing we're going to do is go a little bit of history. C++ has a very long history, and it developed through the 80s, and then about 1990, the International Standards Committee formed to try and get a formal standard coming out. That was successful in producing C++ 1998, which was the first real standard. Everything else before that was de facto. And then 5 years later, we produced what's called Technical Correction 1. So that's a formal update to the standard, but it was mostly a bug fix release. And now we're working on the first major revision of the language, which is currently scheduled to come out in about 2010, where that X is the Roman digit. There are four major thrusts of the language right now. The first one is concurrency, because multicore has arrived. The second one is a lot of cleanup in the language to make programs easier to write and more robust in the face of working programmers. And a major feature is concepts, which helps do type checking for templates. And then we have a significantly expanded standard library that helps us get through all of it. First major topic is concurrency. This work is not something that you would find a big stretch. However, there's an awful lot of details to make it all work together and play together. And none of this is going to be particularly new. Except perhaps in the memory model, which is at the bottom layer here. The first thing is that you don't get to read and write to memory at random once you have threads. You have to control how each thread reads and writes to memory. So if you write in one thread and read from another thread, as in the first example here, that's a data race. Your program is undefined. It could launch the missiles and order anchovy pizza. So don't do that. The procedure to make this work is with release and acquire. So you write to regular variable in one thread. Then you write to an atomic variable with release semantics. Then another thread reads from that same variable with acquire semantics. And now it can see the write to the regular variable that you did earlier. And you can do this with locks as well. But it's very important to note here that you have to use the same variable. Here, we changed from A to B. Those are two different atomic variables. They don't carry that same information. You have to make sure it's the same one. And the atomics have a bunch of useful stuff: reads, writes, atomic increment, atomic XOR. And in addition, we have a compare and swap member function, which allows you to get the full generality of the kinds of things you'd want to do, linked lists, all of that stuff you can now do. And that's designed to work with a loop where you try and figure out what you want and see if you can get to what you want. And there are weaker primitives available for super experts. I won't go into those. Global variables need to be initialized, and once you start having threads, you have to start having initialization scenarios. There's two approaches. One is for regular global variables. The initialization is a bit weaker. So you used to be able to rely on a global variable defined in another translation unit either being fully initialized or being zero initialized. You now cannot rely on that. You have to either not use it or know that it's been initialized. For function local statics, which is something near and dear to the hearts of Google, those initializations are now synchronized. So you can rely on those things being right. The language also has thread local storage. A lot of compilers already have the first line with simple primitive types and pods. That's being formalized and extended to allow types with constructors and destructors. But when you have thread local variables, their addresses are not constant, so you can't use them as arguments to templates. Probably the biggest use of thread local storage is in two areas. One is if you have a multi-process program that you're trying to turn into a multi-threaded program. And the other is for thread local caching. We have mutexes and locks, and there's a distinction here. A mutex is a data object that will live in your objects. A lock is something that is a local variable, and creating the lock then acquires the mutex, and when it goes out of scope, it releases the mutex. You can do that without the lock guard here, but then you have to worry more about exceptions. And a special case of mutexes is the once from pthread. And this has been formalized to be more general than just simple functions. And it says, we're only going to call this argument once. So for any given flag, you'll only fire once. We also have condition variables, which allow you to move locks from one thread to another until certain conditions are met. And in particular, if we have a buffer, there are two conditions that are important to controlling the flow. One is whether or not it's full, and one is whether or not it's empty. And typically, you want to know when it's not full or not empty. And then you can wait for a certain condition to be true, and that has to occur in a loop, reevaluating the condition, because you may get spurious wake-ups. So this is not guaranteed that the condition will be true when you return from the wait, but that it's likely to be true. You still have to test. And then, of course, when you've achieved some condition, you want to make sure that you notify that condition as well. The way we create threads is there's a standard thread class, and then when you construct that thread, you give it something to execute, which could be a function or a class that has a call operator. And once you create that thread, that function starts executing in that thread. And then when you want to synchronize with the termination of that thread, you can join with that thread later. The big problem with threads as they stand is that if you get an exception in here, the exception will then destroy this thread, which will detach the thread. And detached threads have much weaker semantics and are really hard to get a hold of. So you really want to avoid having detached threads. And so those exceptions cause problems. We have mechanisms to deal with that. In particular, you can catch an exception, find out what that current exception is, copy that current exception into a global variable or some other data structure, and then in another thread, you can rethrow that exception, which allows you to catch an exception in a thread and then pass it to another thread to be rethrown, which shows up in futures and so forth. So what happens here is that we are creating our work, and now we have an intermediate. So we create a package task. This wraps the work. And then we will move that task into the thread, and now the thread is executing that task. But before we sent that away, we grabbed a future from that task, which we can now wait on that future and get its value. And if that work happened to throw an exception, when we called the get, we would get that exception. So now we have an exception-safe way to deal with the threads. The next major area of talk is this sort of general bucket of making programs better. And some of it's C99 compatibility, and some of it is just moving around in different areas. The simple things from C99 have been carried forward. All the changes to how integer types work have been carried forward. The preprocessor work has been carried forward, so that's all the same now. And you can write C preprocessor stuff that's agnostic to the language. A lot of the headers have come forward. There are some things in C99 that didn't come forward, in particular variable length arrays. And the reason is the typing of variable length arrays in C is just incompatible with the C++ typing model. Some things that just didn't have enough support to go anywhere, like the restrict qualifier. Compound literals also didn't match C++ semantics. Complex numbers, C++ already had complex. There's been some adjustments, but the basic syntax is still going to be a bit different. The current language only lets you put pods in unions. And that restriction has been eliminated. So you can now put classes with full constructors and destructors inside of unions. But it's not free. Among other things, you have to define the special member functions yourself. So you have to define the default constructor. You have to define the copy constructor. All of that you have to do yourself, because the language doesn't know what to do with it. And when you want to change fields, you can't just assign a new value to the field. You have to first delete the old field and then construct the new field with the placement new. So you have to say, that one's gone, this one's coming into scope. So you have to remember where you were. We also have generalized constant expressions. Now, what this does is basically allow you to have function calls in constant expressions. So we declare a function as something we want to be in constant expressions. The body of it has to consist of a single return statement. And the expression here, assuming the parameters were constant, would have to be a constant. And now we can use this in array declarations. We've extended this to also allow you to create classes that can be constant expressions. So we have a complex number here. We declare its constructor to be a constant expression. And it has to be initialized with full member initializations, and the body has to be empty. And because we have a constant expression class, we can have member functions on that are also constant expression. And we can define a constant p, which is a complex number, and we can initialize that. So now p is a constant expression. And we can use that constant expression later. In particular here, the real member function is a constant expression. So all of this is a constant expression, which means we can now initialize this double statically based on all of that constant expression work following through. And we can extend this with user-defined literals, which is a way to add a little suffix like you see in C with 2.0 f. That f is a suffix that helps you extend the literal space. We can write a function that extends that and recognizes this I as a suffix, matches it to this function, and does the right thing. And so now we can get a full constant expression z that is a constant. And the committee has plans to do ISO units, for length, meters, kilometers in that, but it's not going to be in the current standard. We also have delegated constructors. This has been a long-standing complaint of programmers, where you had to repeat all of the constructors every time, even though one constructor was very similar to another. Now you can define your regular constructor and define new constructors that appeal to the earlier constructor, and just reuse all of that code. Now, it's possible to write mutually recursive delegated constructors. That's undefined behavior. Don't do it. There's been a lot of work trying to regularize and extend the power of initialization syntax. So the current language has like 5 different ways to initialize things. The goal was to get that down to exactly one way. And the syntax we use is these curly braces, basically instead of parentheses or assignment operators. And so we can initialize a variable x with 3 using the curly braces. We can initialize member constructors with the curly braces. And here we have a list. And we can initialize the vector with a list. Think Python here, where you can just write a list and the right things happen. There's one place where we couldn't quite make curly braces do everywhere. And that is that vector its constructor has a parameter to say how big you want the vector to be. Well, we need to distinguish that from how big do you want the vector to be to a vector of one element. So the parentheses here are going to say you want 3 elements. If you were to use braces here, that would say you want a list of one element whose value happens to be 3. Enumerations in the current language are kind of weak because they will decay to an integer at the earliest opportunity. So there's a lot of syntactic problems. We now have stronger enums with this enum class. You can specify the base type. So it's not inferred. You can specify it ahead of time. This allows us to do some forward declarations. You can have the elements as per normal, the enumerators as per normal. But you don't automatically get those enumerators exported to the containing scope. So this is an error because green is not in scope. In order to get to the green, you have to go ahead and qualify that. Likewise, because there's no automatic decay to int, this comparison is wrong because the color yellow is not the same as the alert yellow. Those are 2 different types. The language now has static assertions, which allow us to, at compile time, check certain things. So this template parameter, we want to make sure it's greater than 3. We say that with a static assert. And this text message is what comes out in the error diagnostics from the compiler. We can now say, I want the default behavior. So in the past, there's always a big fight over whether or not you declare the default constructor and so that everybody knows you've thought about it, versus not declaring it and getting efficiency. Well, now you can get both. This says, I want the efficiency, and use the default behavior. This is particularly important when you want to have a user-defined copy constructor, but still want the default constructor. There's no way to do that in the current language. Likewise, we have it for the copy assignment operator and the destructor. We also allow you to get the default behavior without having it be trivial. So the problem with writing this is you're now committed. That's part of the ABI. If you don't want to commit to it in the ABI, you sort of have to write a non-trivial constructor. this allows you to write that non-committed interface and still get the default implementation. The language also has move semantics, which is implemented with a language feature called R-value references, which is a kind of tricky feature. But basically what it allows you to do is have structures that are moved rather than repeatedly copied. And this can substantially improve the efficiency of code, particularly things that want to write in a functional style. Or that where you don't really want multiple copies of something. So here we have a wrapper for file star, and we don't want, there's no suitable default. We don't want to copy it, so what we're doing is we're deleting that function. The symbol still exists, but if you try to call it, that's an ill-formed program, and the compiler will catch that. And here we have a move constructor. What this says is, I will only accept parameters that are sort of R values and not L values. And then we can close that file. And here, we're opening a file foo, and the pushback operation is declared to take an R value reference parameter, so it can now move from the file created. This allows us to shuffle data through many call parameters, without actually doing any significant copying. We also have explicit conversion operators. So given this class here with its conversion operators and these two functions, this call would be ambiguous, because there are two matching conversion operators. And sometimes you don't get the right ones. So if we redefine those conversion operators and make one of them explicit, now if we do this call, the explicit one doesn't apply, because this is an implicit conversion. So it can only be this one, and the conversion goes through. What's probably better is that if you make both of them explicit, so that the right things happen. So typically, you only ever want one of these to be not explicit, and all the others should be explicit. The language also does a better job of type inference. So a common thing you'll see in C++ code is these common sub-expressions, pf, pf, with different trailing function calls. And this occurs a lot because people don't want to figure out what the return type of f is and write that, and so forth. So we get a lot of duplicate execution of code. Now we can make the type specifier be auto, and this says, infer the type of auto from the return type of this expression. And now we can go ahead and use this variable later and avoid the redundant call to f. Sort of simple, don't have to think about it way to optimize your code. We also have what's called late specified return types. The problem with putting the return type in front of the function is that if you want to infer the return type from the argument types, you're out of scope. The arguments aren't in scope yet. So we now can move the return type to the end of the function, and we can then use the decal type, sort of like the GCC feature, to compute the type from the arguments, and away we go. Now, there's still a little bit of debate about the exact syntax here, and that will get resolved before the final language. We also have a new style of for statement, which infers the appropriate iterators and ranges and so forth. So given an array, this will do the appropriate inference for iterators, and you can run the body. And it's even more powerful when you combine that with the auto keyword. So we can take some data structure. We don't even have to know what the elements of the data structure are right now. Say we want auto reference to each of those, and then we can modify those.
On the previous slide, you had P pointer to F. I noticed that at the end you had auto followed by an ampersand, but at the beginning you didn't. If P pointer to F returns a reference, does that first auto variable also a reference, or is it not a reference?
It's not a reference. So the next major feature of the language is Lambda expressions. So this is the Lambda introducer, which says here's a Lambda coming, and then the parameters to the invocation of the Lambda and the body of the Lambda. This Lambda introducer also allows you to specify a capture list. This says, what do you do about the containing environment? That ampersand says, OK, I want to get to the containing environment by reference, which means that if we were to modify min salary here, that would be reflected in the environment. I can alternatively say, well, I want to capture min salary. So when I create the Lambda expression, the closure, this will be captured, and it won't change. So if I try to modify min salary in here, it will actually not escape the Lambda. So that gives you a great deal of control over what you do about your referencing environment. This is good if you're trying to simulate something like a traditional C for loop. Capturing variables is good in a multi-threaded context where you really don't want a lot of concurrent access to the environment. And then there are a number of syntactic improvements that have been dropping in. One is being able to put the two angle brackets right next to each other. There's now a syntactic name for the null pointer instead of doing inference on 0. You can apply size of to member variables. There's now a full attribute syntax, which allows you to sort of get away from all of the vendor-specific ways to write attributes and go to a standard way. And I'm going to hand it over to my colleague, Matt Austern.
Yeah. Well, Doug Greger came here last year and spent a hour-long talk on concepts. I'm going to have about 5 minutes, so let's try to get going quickly. So first thing to know about concepts is, in a sense, they're a language feature. In a sense, they're also something that we have in any language, not just in C++. People started thinking about this idea in the context of scheme and data and all sorts of other languages, and we've always had them. The basic idea of, let's say, this style of programming, of generic programming, is you classify the things that you're talking about. What's the fundamental category? You write algorithms in an abstract sense instead of relying on the details of any individual one of these things. And then you write specific models that conform to these abstract concepts. This is the way mathematics has always worked, and this is essentially programming as mathematics. Well, that works reasonably well, whether you have language support for it or not. But we found in the context of C++ that we really do want language support for it. In C++, the way we typically think of this kind of programming is with templates. And templates just need a little bit of taming. So one way to think about concepts as the language feature is that they're constrained genericity. You can think of them as type classes. If you're a Haskell fan, you can think of them as types of types. So let's first talk about why we need them. What's painful about programming in C++ templates as it stands right now? Well, the first thing is we've written this very nice template. Here copies things from an input range to an output range. What are the requirements on this? If I'm a user and I want to plug classes and objects in here, what do I have to do for it not to explode? I haven't told you. I've just given you names here. If you happen to be familiar with the naming conventions of STL, then you can make a pretty good guess. Or you can read the implementation and just figure out something that'll satisfy this implementation. I'm really not a fan of requirements that can only be expressed in comments or naming conventions or where you have to read the implementation. Requirements ought to be in signatures, and here they're not. So another pretty painful thing, let's suppose that you are familiar with STL. You know that sort takes iterators. So you know if I want to sort a range, I pass it a couple of iterators. OK, well, you're not super familiar with STL, so you know that you have to pass in iterators, but you don't happen to know that list provides the wrong kind of iterator. Oops. I was actually a little pleasantly surprised. GCC has gotten better. Now it only provides 18 lines of error messages for this. Unfortunately, even though GCC has gotten a little bit better, something you don't get in these 18 lines is the one fundamental thing: you passed in the wrong kind of iterator. You should be passing in a random access iterator. And that's a problem, too. We don't have a way of specifying this in the language itself, so the compiler doesn't have a way of talking about it. And then the third problem is when you do get these errors, they come too late. Everyone sees the bug in this code, right? It's just glaringly obvious. This is the bug. That should be bang equals, not less than. And the bug here is that this actually would be correct if we were taking in random access iterators. Instead, we're taking in input iterators. But oops, the compiler doesn't have any way to know that, because input iterator is just a name. The compiler doesn't know there's anything special about that. So we've got this mismatch. And the worst thing about this bug is it won't show up in testing, because probably when you test this, you're going to give it vector iterators to try out, and it'll work. And it'll only be a month later when some unlucky user sees the problem in their code. So what does this look like with concepts? What we want to do is actually constrain what a template parameter can be instantiated with. You have to say something about what the types are in these case. And here's the syntax for doing it. We're saying, I have a concept less than comparable. And any type that conforms to that concept has to provide this kind of operation. This is simple. This is very simplistic, by the way. First of all, it's a simple concept. And second of all, it's not actually even enough constraints for this very simple concept. But you do what you can to get things onto a single slide. So here's how you use a concept to constrain code. You've got about the simplest kind of operation that you can imagine that requires less than comparison. You take two objects, return the smaller of them. And this is very simple, but it provides the error checking that you want. If when I'm writing this function, I make a mistake, if I perform some operation here that the concept doesn't guarantee is there, I will get an error, and the error will be, you've used something that isn't in the concept. So that last example where I used the less than by mistake, that's taken care of. The way you use this is the same way you use any other template. You just call the function. And if you are calling it with a type that does not conform to this concept, you will get an error message. You've passed in the wrong type. You need to pass in a less than comparable type. You haven't. And before I move on to the next slide, notice this one word here, auto. That word auto means if a type provides the appropriate operations, then we automatically agree that it conforms to the concept. That's not always what you want. It's fine for a case where you've just got less than, greater than. You don't want to go through the nuisance of specifying for every class you define that it conforms to less than comparable, equality comparable is copyable, blah, blah. But for a bigger type like, say, an iterator, then it probably is good for you to express your intentions explicitly. You've written some kind of an iterator. I've put in a bunch of ellipses here because an iterator is a fairly large class, even in a simple case. And the way you explicitly declare your intentions then, the way you explicitly say that this conforms to the forward iterator concept is with the concept map keyword. You're explicitly saying, my type conforms to forward iterator. And ultimately, that's all that it comes down to. You declare concept, a set of requirements. There's special syntax for doing that. You declare when you define a template what the concepts are that the template parameters have to conform to. And when you define a class, if appropriate, you say which concepts they conform to. There are a whole lot of other features with concepts, some of which I expect will be used commonly, some of which I expect will only be used by experts in rare circumstances. Just to name a few of the more important ones, we've got refinement or concept inheritance. You can say anything that conforms to this concept also conforms to that one. If you're familiar with the STL, the sort of classic example of this is the iterator hierarchy. You want to have the random access iterator concept inherit from the forward iterator concept. I showed you the simplest kind of requirement on types, just saying that a template parameter has to conform to a concept. There are more complicated cases where you have multiple template parameters and there has to be some kind of a relationship between them. That's what the requires keyword is for. And Then the concept map keyword, I showed how you can use it to say that a type conforms to a particular concept. There's also a sort of interesting case. What happens if a type in some philosophical sense conforms to a concept, but doesn't have exactly the right syntax? And the classic example here again is from iterators. You want to be able to say that pointers are random access iterators, but pointers don't have member functions. So you have to say a little bit about how the syntax maps from one to the other. And that's what the other feature of concept mapping is for. That's how syntax adaptation works. And I think that my 5 minutes are up. So if you want to know more about concepts, ask us after the talk, or go watch Doug's talk again, or wait for the tutorials to get written. So there have been other new template features. Concepts are the one that probably took the committee the most time. I think it's actually fair to say concepts were 10 years in the making. But there have been other interesting template features. And the one that is actually worth, well, I'm going to mention to actually spend some time on one. This falls into the category of, why didn't you do that earlier? It's a restriction that there was never any really good reason for, that you couldn't have template type defs. Well, now you can. The syntax looks a little bit funny for uninteresting historical reasons, but the feature is there. Something that's a little more interesting is variadic templates. So again, the first question isn't so much how the feature works, but why do you care about it? Why is this something you would want? Well, this is the classic example. You'd like to have a tuple type, and you'd like to just be able, well, it's obvious what it does. It's an obvious generalization of pair. Pair takes 2 template arguments, stores 2 things of arbitrary types. This takes n arguments, stores n things of arbitrary types. It is actually possible to implement this without variadic templates, but it is extraordinarily ugly, and there are limitations. This is really the way that you want to do it. Another pretty obvious example, you'd like to be able to pass in n arguments and find the minimum of them. And a slightly less obvious but still interesting example is, type safe printf. This probably looks pretty familiar to you if you've got Python. We've got 3%s things here, and the semantics is just you can pass in anything that converts to a string. The conversion will happen at compile time. It will just work. So how does it work? Well, if you're actually defining variadic templates, if you've used Haskell or ML, it'll actually look fairly familiar to you. It's pattern matching. This is a variadic template declaration. It says that you can have an arbitrary number of arguments, and then you have to define partial specializations. This is where the pattern matching comes in. Here's a partial specialization for the case where there is at least one template argument provided here. We've now named that head. You can do something with it. Here's all of the rest of them. You then recursively invoke the template again. And finally, it bottoms out because here's the specialization for where there are no arguments. And you can use various tricks for how you work with one argument at a time. I'm not going to go into this in detail, but if you're familiar with this sort of pattern matching style of programming, it should be fairly obvious. Well, that's all I'm going to say about template features now. So we've got about 5 minutes now to talk about everything in the library. The library is now about twice as large as it was in C++ 98. And the one-line description of what's in the library is everything in TR1 except special functions, sort of, and then just a few other things. So this list even isn't quite complete, but it contains most of it. And I'm just going to touch on a few of the highlights. This regular expressions, it's not as if nobody has been using regular expressions in C++ before, but there have been a whole bunch of different libraries, none of them standard. And this is the standard syntax for doing it. Again, if you're used to Python, it should look fairly familiar. It's more the Python model than the Perl model. You have a regex class. You invoke it. You invoke the constructor, passing in a pattern for the regular expression. And oh yes, here's another language feature that we hadn't mentioned before. You see this R here before the string literal? This is a raw string. And in a raw string, you don't have to escape backslashes, and you can put in new lines. Having regular expressions without that would have been pretty painful. So you create a regular expression pattern. You invoke the match function on the input, the pattern, and a object here that gives you access to the individual fields, then you can just extract each of the individual fields you care about. And of course, there are more things that you can do. It's got search and replace or format, depending on which way you want to think about regular expressions. We can iterate through matches, match one thing, then match another thing, then match another thing. But in the simplest case, it's really as simple as this. Random numbers. Again, it's not as if we haven't been using random numbers in C++ since forever. We've had the rand function. The model here is we want to distinguish between the engines. Where do you actually have your underlying source of randomness? Is it linear congruential? Is it Mersenne twister? Is it some kind of physical entropy generation? And then once you have this physical source of randomness, how do you actually get a set of numbers distributed in some pattern? You've got the uniform distribution, you've got the exponential distribution, Poisson, normal, log normal, all of these things. So here's a simple example where we take one engine. This is recommended as the one to use if you don't want to think about it too hard. It's just a reasonable default. You've got a distribution here, a normal distribution. Here are the parameters. And you get a number, or, well, presumably more than one number from that. Smart pointers. These are pretty familiar from TR1. We've got the shared pointer model, which is simple reference counting. If you make a copy of a shared pointer, then they point to the same thing, and the underlying object gets deleted when the last smart pointer to it disappears. Unique pointer is a little bit less familiar because you couldn't have it without the move semantics that was introduced in C++ OX and that Lawrence talked about. Unique pointer, the model is an object is owned just by a single smart pointer, but that pointer can change. You cannot make a copy of a unique pointer because then the ownership wouldn't be unique, but you can do a move. So here's an example, again, of how you might use unique pointer. We have a function that creates something. There's a temporary variable of type unique pointer in here, but it goes away when you return it, so it's still unique. You have a vector of unique pointers. You can push something into the vector. At any moment, the ownership is still unique. At any moment, there is still only one owner, but that owner can change over time. No copy, but move. And I think at Google, that's probably going to be fairly popular since the moving but no copying is a fairly common technique here. Whole lot of new features to support manipulating function objects. I'm not going to go into all of them in detail, just show a simple example that combines a lot of them. This is a way of naming an arbitrary function-like thing that takes a single argument of type person, returns a string, and this can bind to a member function. It can bind to a function object. It can bind to an ordinary C-style function. This just abstracts away all of these differences and just lets you talk about the argument types and the return type. And here is an example of how you can use this to return something that takes a string and returns a bool. And that's a result of a fairly complicated bind expression that lets you test whether a person has a name equal to something arbitrary that's passed in. This whole bind facility is probably largely redundant now that we have lambdas. There might still be cases where it's more useful than lambdas. I can't actually think of very many. This is probably still useful. It really is useful to be able to talk about function-like things without the specifics of the syntax. We've got some very, very limited support for talking about time. This was really an adjunct to the threads facility because you really like to be able to say when you're talking about threads, run this in 5 seconds, sleep until such and such a time. It can be the basis for a more complicated time library, but at the moment let's think about it. Let's think of it as a somewhat more explicit and somewhat more type-safe way to talk about clocks. And it's a little bit more explicit, mostly because, again, the question of what a clock represents, you've got this integer. Is that microseconds, milliseconds, nanoseconds, what have you? Now you're actually able to talk about that in the type system. So it's at least a slight improvement over what we had before, and it's something we can build on. Well, a whole lot more library features that I'm not going to talk about. You can ask us later or again, read things. Probably the most interesting of the things that I've left out are improved Unicode support. We've got new types to represent wide characters. We've got them extended into the library somewhat. We've got some features for converting between UTF-8 and UTF-16 and UTF-32. And we've made some other relatively minor improvements in string. Notably, we've made it a little bit less thread unfriendly. So, a whole lot of things that didn't get into C++ OX. Suddenly, the committee has started feeling time very short. This is a list of some of the things that didn't get in, but that the committee is reasonably committed to towards the future. Probably what's going to happen is the next major revision of the standard will still be a while from now, but we're going to be releasing these things as technical reports one at a time. Those won't officially be normative, but it'll at least be a way to design and describe the features so that compiler writers can get practice implementing them. And everyone has their own hot list of what features they think are most interesting from this list. I suppose I would probably have to say that improved thread support would be at the top of my list. We've got very limited support for higher order concurrent programming in the C++ standard. It's not really much higher level than POSIX threads. You can create threads, you can do locks, you've got condition variables, but we don't have all of the other data structures that we're used to. We don't have thread-safe queues, we don't have thread pools. It would be very nice if we could standardize those things using our low-level thread structures as a foundation. And that's something where I would hope that Google can help by defining some of these facilities and open sourcing them and trying to get them standardized. So what is happening now? Well, officially, C++ OX has not been released yet. And in fact, I should take out that word officially. It just isn't finished yet. What we have right now is called a committee draft, meaning this is the first draft of the new standard that the committee is even willing to talk about in public. And now we're in the middle of the public comment period. We're asking for people to find bugs in the standard, find features that should be removed, find some features that aren't as complete as they should be. Notice the deadline. There is a reason that this is in red. We have some time to submit public comments. Lawrence and I are collecting them. I'll tell you in a minute some ways that you can help with this. And we should try to get them in soon. What's going to happen after this is the standards committee is going to look at all of the defects that have been reported. It's going to look at all of the defects that committee members have found on their own. And it's just going to be, well, you can think of the CD as an alpha. So what we want to have 1 year from now is our beta, the final committee draft. There are still going to be some more comments on that, but we expect them to be much smaller. We expect that here things are going to be really feature complete, and it's going to be small bugs that we're looking for. A year after that, we will be shipping the final draft international standard. That's still not officially a standard, but except for typos, you should think of this as final. It's just going to take 6 months or a year after that for it to get through all of the official ISO bureaucracy. So I think we've left enough time for questions now. And I would encourage everybody to use the mic for questions, since some people are listening to this talk remotely.
I think between the two of you, you have a reasonable idea of what the C compiler team is up to, what GCC is up to, and kind of how the C-style people think. So when do you think we might be able to start using some of these in conforming Google 3 code? At least some fun subset of them.
I think that some of these features will be easier than others. One problem, of course, is that we use more than one compiler at Google. So we're not going to be able to use any feature until, let's put it generally, until whatever code that feature is in can be compiled by all of the compilers that are ever going to be touching that code. That's probably the biggest concern, because it's a big company and we don't necessarily, there isn't necessarily a single person who even knows what all of the compilers are out there. And if we solve that procedural concern, we'll probably be able to get these features into use sooner. The style issue, well, some of these features are going to be a little bit more controversial than others. I would expect that say auto, there probably is going to be very little resistance to. I would expect that some of these features address areas of the language that Google just stays away from in generals, and that probably won't change very quickly.
So currently, C++ is the slowest compiling language that I use. How do you expect these changes to affect the speed of compilation?
So the speed of the compilation will go down. The current estimate, a lot of it comes from the concepts and the improved checking on the templates. The current expectation is that in full production compilers, there will be about a 10% loss in performance for code that uses the standard library in a heavy way. For code that doesn't use the standard library and isn't using these features, you probably won't see a major slowdown in the compilation.
The other answer that I should give to that is that the range of compilation speed in different compilers is much larger than you might think. We used to work at Apple before I came here, and people at Apple were constantly comparing the speed of GCC and MetroWorks and wondering why GCC couldn't be anywhere near the speed of CodeWarrior. I am hoping that it would probably be hard to modify GCC to match that speed, but other compilers that are better than GCC are entirely practical, and there is work on new C++ front ends.
I'd also like to point out that for optimized builds, most of the compilation time is in the back end and the optimization and so forth. So the front end speed is really only an issue when you're doing debug compilations.
Yeah, 2 quick questions. I'm glad to see they address the thread safety of the strings. Does that mean that the copy on write is gone? Are they using the atomics for that? And also, what about other reference counted semantics like locales and facets?
Strings, copy on write is gone. So yes, that's the existing standard has very complicated guarantees that were basically designed to allow but not require copy on write. The new standard has guarantees that I think basically cannot be satisfied with copy on write. That doesn't bother me. Copy on write is one of these things that sounded like a great performance improvement at first, but that most library vendors have decided to move away from anyway. And the question is, what about other reference counted facilities? Shared pointer is just plain thread safe. It's designed to be, it uses, every implementation that I know of uses atomics internally. Locales and facets, trying to think what terminology to use here. There is a general guarantee of thread safety in the library introduction. Essentially, unless anybody says otherwise, using 2 objects of the same class in 2 different parts of the program in 2 different threads, it won't explode. And the implementation has to do whatever is necessary to meet that guarantee.
A question here. Is there going to be template specializations based on concept conformity? So could you have sort work for linked list just as well, but at performance hit?
Yes, that was on the list of other concept features that I would not discuss. I think of it more as overloading on concepts, and it's actually a pretty essential feature. One of the classic examples of why you need this is in the existing STL. We've got this advance that takes an iterator and a count. If it's a forward iterator, you just have to advance it one at a time. If it's a random access iterator, you just add. So yes, you can do that overloading.
Is the committee considering any actions that would make C++ easier to parse for automatic refactoring tools?
So the problem with that is that it's very difficult to make C++ easier to parse and make it compatible with the past. So the general approach of the committee is to try not to make it too much worse. So it's part of the price of dealing with 1 trillion lines of code.
It's very hard to remove features. There's one feature that wasn't necessarily the feature I hate the most, but it's on my list, and it's one that I thought was completely unused, so I proposed to the committee that we get rid of it. And the IBM rep said, no, no, we have all of this code internally that you can't find with Google code search that we would break if we removed that. So we are still going to have trigraphs. And if you can't even get rid of trigraphs, you can't get rid of anything.
Oh, please.
OK. So with the introduction of threads, and especially all of the mutexes and condition variables, was thought given to the ability to automatically do thread safety reasoning?
Well, the GCC compiler has facilities in it to annotate the association between variables and locks and so forth. So that stuff is going forward. There's no specific language design feature to address that, but it was in the mind of the people putting this together that should be possible.
C++ is my preferred language for more than 10 years. And usually when people complained that C++ was complicated and complex, I used to explain that as kind of misperception. It's a lengthy, I won't give it here. But now that the new standard is almost twice long than the old one, isn't that too complex? Was the committee considered this situation?
Okay, so there's a couple of answers there. First is the standard is much bigger, but most of the growth has been in the library. So and that's fairly isolated. You could not read a chapter and not be upset. The core language part has grown, but it hasn't grown a whole lot.
The third answer is everybody on the committee agrees that C++ is too large now. I mean everybody, it's unanimous. Everybody agrees that we shouldn't add too many features, and everybody says, but just this one feature. And we've tried to strike a balance between restraint and growth. I hope we've struck the right balance. There are some features we've added that I wish we hadn't, but not very many. And
the other thing to remember is many of the features that have been added are in the way of generalizing things. So C++ 98, if you try and mix this feature and that feature, you find out, well, you can't really do that. And so a lot of the complexity comes in things you couldn't do. And a lot of those barriers have been reduced. The initialization, you could simply not learn the old way to do initialization and go with a new syntax and cover almost all of your needs. There are simpler ways to approach the language, but if you want to know the whole language, it has gotten a little bit more complicated.
Mutexes reentrant. Mutexes reentrant.
Oh.
So there are regular mutexes, timed mutexes, and reentrant mutexes, and timed reentrant mutexes. What we don't have is reader-writer locks. That was something the committee decided they didn't have enough time to put into this standard.
I think it's fantastic work. I haven't looked at this for a long time, and just surprising the number of features you put in this. How are you going to name this new language? More seriously, the perfect forwarding issue, is that going to be taken care of? The reference to a reference and all that?
Our value references, one of the design goals for our value references was to take care of that problem, yes.
And that's used heavily in the standard library now.
I think we're out of time now. So,
thank you very much.